Good morning, listeners, and welcome again to today's class. Today, we intend to solve with you a real life example on regression, correlation, and coefficient of determination. In our last class, we called up these concepts or topics and discussed elaborately with you, giving formulas or estimators of calculating them from a data set. But we could not exhaust all what we were expected to do in that class, which included solving a real life example. So, as a continuation of that class on regression, correlation, and coefficient of determination, we intend to draw up an example, a real life example, and solve as many questions as possible as they could ask us when we are given a real life data. This data we are going to call up is bordering on the reading hours of students and then the corresponding test scores that they have on a particular subject which they prepared for. So permit me to call the question here up on the board while we begin to solve all the questions that they will be asking us together. Without wasting much of your time, let us call the question up on the board. Like I earlier had mentioned, the question is on the reading hours of the students and then their corresponding performance in a particular test that is scored all over 20. So permit me to write reading hours here. This is my reading hours. Let me now put what hours? Study. What I mean by this is what reading hours. Then permit me to talk about what we call the test scores. The test scores, I have this and I have this. So I have this and I have this. Okay? So here I have values. Here I have what? 0. I have here 3. I have here what? 1. I have here 3. I have here what? 2. And I have here what? 5. I have here what? 3. I have here what? 6. I have here what? 4. And I have here what? 7. I have here what? 5. And I have here what? 9. I have here 6. And I have here what? 9.5. This is the question that they gave us, or the data set that they gave us. The first question says, and I read, obtain the estimate of the regression parameters beta 0 and beta. That is the first thing that is before us. The first question says, you can take it down, obtain the estimate of the regression parameters beta 0 and beta estimates. So in a way of solving this problem, I will recall for you the estimate of the regression parameters which we stated the last class. The regression equation or the regression model is given as that y is given as beta 0 plus what? Beta x plus what? Error 10. This is what we call the regression model. And of course, a simple linear regression model. Simple because only two variables are involved here, the dependent variable y and the independent variable what? X. Linear in the sense that the relationship between y and x is represented with a linear model or with a line. Okay? So the next thing here is what becomes a regression equation. Regression equation is when you have estimated the values of this beta 0 and beta, and you have now replaced them into the what? Into the equation. And therefore, what we have here becomes what? Y cap is given as what? Beta what? 0 what? Cap plus what? Beta what? Cap x. What we are calling cap is what? Is estimate. That we have known the true value of this beta 0 from this data, and you have known the value of this what? Beta from this what? Data. So you are saying beta 0 estimate, beta estimate computed from this what? Data set. Which means this beta 0 and beta are what is called the regression parameters. And the first question asked us that we should obtain the estimate of the regression parameters. This is what we call the estimate. The beta zero cap and the beta cap is what we call the regression, the estimate of the regression what parameters. The question becomes, what is the formula with which we are going to obtain the what the beta zero, and what is the formula with which we are going to obtain the what the beta, using what we call the ordinary least square method. So I will now write the formula on the board. All of us will now move together. Do remember that the formula I gave us in our last class says that my beta, ordinary beta, this my beta cap, talking about this, is given as what? N summation of x, y, minus summation of what? X, summation of y, all over. We have n summation of x all squared minus summation of x all raised to power what? 2. This is the formula which we gave, which we called the ordinary least square estimator of the slope of the regression what? Equation. So I am going to use this formula now in order to obtain this what? Estimates. Then I will now come back now to the question given to me. When I come back to this question given to me, I will find out I have what? Of course, we know that coming from this data now, without being told, the performance of a student is going to be dependent on the reading hours of that student. So we are going to use what? The reading hours now to be the independent variable x, and we are going to use what? The test scores now to be the dependent variable what? Y. Because this test score is expected to depend on the reading hours. And then the reading hours are expected to influence the test scores. That's what we call the effect of the reading hours now on that what? Performance. So without being told, this my hours of study is X, and this my test score is what? Is Y. So I am going to come here and write my what? My X, write my X and write my what? My Y. So when I write my x, the value of x here is what? Is 0. The value here is what? 1. Value here is what? 2. Here is 3. Here is 4. Here is 5. Here is what? 6. Then the corresponding value of y here is what? 3. Here is what? 3. Here is what? 5. Here is what? 6. Here is what? 7. Here is what? 9. And then here is a 9.5. Then I'll draw a line this way, draw a line this way. Now, if you look at this estimator or this equation, you find out, or formula, you find out that there is a column or there is a term xy. So I need to include xy in this my data set if I must have to evaluate this. So I will now come and create another column talking about what? X, what, y. This xy is now going to be, I will use this value and multiply this value, give this value. So 0 times 3 is what? 0. 1 times 3 is what? 3. 2 times 5 is what? Is 2 times 5 is what? 10. 3 times this is what? 18. Then we now have 4 times this, which will give me what? 20 what? 8. Then we now have 5 times 9, which will give me 45. And then 6 times this, which will give me, I think, 50 what? 7. If care is not taken, 57. You can use your, of course, your data. I'm using just off head to do this calculation. You can use your calculators or any calculating device to cross check whether the values we are getting are the same. Then when we now come here, we are talking about what? X squared. So I need to include another column talking about what? X squared, and I'll have a column like this. I will pick each of the value of x, I will square it here. So I'll have 0 squared is what? 0. 1 squared is what? 1. 2 squared is what? 4. 3 squared is what? 9. 4 squared is what? 16. 5 squared is what? 20 what? 5. And then I have that 6 squared is what? Is 30 what? 6. That's the value I have. So what am I going to do? I will underline this way. I will underline it this way. I will sum all this value, write it here, sum all this value, write it here, sum all this value, write it here, sum all this value, write it here. To save your time, these values have been solved and written down. So I'm going to call the sum from the book here, and then drop the answers here while we solve here together. So the value when you sum all this one here will give you 21. The value when you sum y will give you 42.5. The value when you sum xy will give you 161. And then the value when you sum x squared will give you 91. These are the values you have. So with this, we now come back here because we want to sum this. We ask ourselves, there is a value here, or there is a term here, n. And this n is talking about the number of the data sets. Then I will now come and count the number of my data sets. I have 1, 2, 3, 4, 5, 6, 7. Okay? Which means this my n is given as what? This is given as what? 7 multiplied by. My summation of xy, here is my xy. These are their values. The sum of xy, that is summing all the value here, give me 161. So I will now come here and put what? 161. The sign here is what? Minus. Then x. Look at the values of what? Of x. When I sum all the x, the value is what? 21. Then I now have what? 21 multiplied by. I come. I'm talking about the value of y. I will sum all the value of this y. The value is what? 42.5. Then I have what? 42.5 all over. Here is my n still, and my n is 7. So I will now put 7 multiplied by. Here is my x raised to power what? 2. That is, I'll come here. These are my x raised to power 2. And when you sum all these values for x raised to power 2, it gave me 91. So I have that here is what? 91 minus. Here is what? Summation of x. And my summation of x is what? Is 21. Just that it is what? Squared. So you are going to have what? 21 all raised to power what? 2. And then to avoid wasting your time pressing calculator, seeing that the value of this and this, we have computed the value of this now and drop the final answer. So what is expected of you is to pick up your calculator or any of your calculating device and be able now to evaluate this quantity to know whether it is going to give you exactly what we have. Because the answer which we have here is given as, 1.1964. So we expect you now to evaluate this quantity to be able to know whether you are going to get 1.1964. That is the value of our beta curve estimate. That's what we call beta estimate. Now, having gotten the value of this, we are yet to get the value of the intercept, which is the beta zero estimate. And of course, we also gave the formula in our previous class that the beta zero estimate is given as beta zero estimate. Beta zero estimate is given as y bar minus what? Beta what? X means or what? X bar. That is, y bar means the mean of the dependent variable. And then our beta estimate is the value of this slope which we have computed, and then our x bar is talking about what? The mean of our independent variable. And of course, this mean y bar can be written as, this is summation of y all over n minus. Here is my beta estimate, which is beta estimate. X bar means what? Summation of x all over what? N. We now come back here and ask ourselves, where is our y? These are going for y. But we have summed all this y and we have got 42.5. So summation of y is given as what? 42.5 all over. The data point is given as what? 7 minus. Of course, this beta estimate is of course computed to be 1.1964 multiplied by. Summation of x, we come back here and look at our x. Summation of x means summing all this value, and we got it now to be what? 21. So I will be able to have what? 21 all over. Of course, our n remains what? 7. Without wasting much of your time, as in picking calculator and pressing this and this minus this, we have computed this value and dropped the final answer. So what we expect you to do is, on the course of this class, pick up your calculating device and then evaluate this and know whether you are going to have the same thing with what we have. Because the final answer is, what we have is that this is given as 1.4567. 1.4567. So that is the value of our beta zero cap. So that answers the question number 1 that says obtain the estimate of the regression equation or obtain the estimate of the regression parameters. This is the estimate of the slope, which is called beta. This is the estimate of the intercept, which is called beta zero. And of course, look at them here, beta zero estimate and then beta estimates. That is the question number 1. Then question number 2 here says, and I read. Question number 2 says here, and I read. Explain. No, the question number 2 says, explain the nature of the relationship between X and Y. Explain the nature of the relationship between X and Y. You can easily understand the nature of the relationship between X and Y by looking at the value of the slope, which is the beta estimate. I did mention in our last class that the moment you calculate this your slope and the value of your slope turns to be what? Positive. It means that there is a positive relationship between X and what? Y. But when a value of your slope turns to be what? To be negative, it means that there is a negative relationship between X and what? And Y. And looking at the value of our own slope, it is 1.1964, which is a positive what? Quantity. So conclusively, one can say, or one says, that there is a positive relationship between the reading hours of what of students and their test scores. And then under normal circumstances, it is expected that we have a positive relationship between the reading hours of what of a student and then the test score. The higher the reading hours, if all things are equal, the more the student performs in what? In the test. And then the lower the reading hours now, the lesser the student perform in the what? In the test. If every other variations are held constant. So that is what they ask us what in the to explain the nature of the relationship. And then looking at the slope at the intercept equally, we see that the value is what is positive, which tells us that the value of what of the test score is still going to be what positive, even when the reading hours is what is 0. And of course, this is seen very, very clear here that this is what even 0 here. And when here is 0, we can even see that the value of the test score of a student is what is 3. That is to say that even when the student did not prepare at all, there is a chance of the student going to score something in the what in the test. That is what we mean by this intercept. The intercept is what is positive, giving a value of 1.4 thereabout and thereabout. So that's what we mean by this. This is as a result of the data set which we have at hand. Okay? Then we move over to question number 3. Question number 3 says, and I read, fit the OLS regression line or equation with your calculated beta 0 and beta. That is, fit the regression equation using the ordinary least square method. That's what they mean by OLS. It's not a problem you are going to begin to scratch your head or your head. It is just for you to look up here. This is now the regression equation. And then you use your OLS method to arrive at this equation which gave you this. You equally use your OLS method to which is this, to arrive at what this is quantity. So they want you now to fit the regression line. So or equation, you come here. So your regression equation is going to be, you have that your what? Your Y estimate, which is this, is given as. The value of your beta 0 estimate is 1.4. So you have 1.14567. The sign here is what? Is plus. What is this value? It is what? 1.1964. What you have here? What you have here is what is your X. So that is what they refer to as your OLS regression equation or regression line, which you have fitted because you now know the true value of your what? Beta 0 and your what? Your what? Beta, which is their estimates are beta 0 estimate and beta estimates, which is what you have computed now and you have replaced in this equation. So that is what they refer to as the OLS, ordinary least square equation. That is talking about question number 3. Remember, we have answered 3 questions. The first question says, we should obtain the estimate of the regression parameters, beta 0 and beta. These are beta 1.1964. These are beta 0 estimates 1.4567. The second question says we should explain the nature of the relationship that exists between x and y. We quickly told ourselves that for us to answer that question clearly, we should look at the value or the nature of the value of what of the slope, which is what the beta. The value of this what beta estimate is what 1.1964, which is what positive. And we say that if the slope is positive, there is a positive relationship. But if the slope is negative, there is a negative relationship. So going by this, which we have, the answer here is what positive. Therefore, there is a positive relationship between the reading hours of what of the student and then their test scores. Then the next question asked us, now, or even before that next question, of course, when we equally look at what our intercept, we found out that our intercept means that it is what? It is 0. It is what? Positive. So by implication, even when there is no reading hours of what of the student at all, it is expected that that student is going to get something in that test. Then the third question asks us that we should fit the regression what equation using the value of our regression what estimates. We now reminded ourselves that look at our what our regression what equation. Our beta 0 cap is already this, and our beta cap is already this. So you just expected for you to carry this, put in place of this, and carry this and put in place of this, and include your x and y. That is what I have here. And this is what we call the regression equation. Okay? So thank you thus far. Let us call the next question which they ask us. The next question they ask us, they say, what is the estimate of the dependent variable? Which is, what is the estimate of the test score when the reading hours is what is 10, when the reading hours is what is 12, and when the reading hours is what is 14. What is likely going to be the performance of what of the student in the what in the test? If such a student increases his reading hours up to 10 hours, increases his reading hours up to 12 hours, and increasing his reading hours up to 14 hours. And that was why in our last class we did mention that we can use the regression model or equation to forecast the value of what of a variable. Okay, so what we are going to do is to clean the board now and be able now to tell ourselves or work with you the possible test scores of the students when their reading hours become 10, 12, and 14. Thank you very much. So permit me to clean here. We are going to answer that question favorably by using this value which we have here. We are going to answer it favorably by using what we have here. So we are looking at the value of y, because that's the question they ask us now. To get values of y, values of y, when x equals what? 10, 12, and what? 14. That's what they mean by that. So what we are going to do is this. We now come, we write it what? Y this way. We write what? Y this way. Then we put what? Cap. We now put like what? 10. What we are writing this thing to mean is the value of this y when the independent variable, which is the reading hours, is what is 10. That's what we mean by this in which we wrote like this. And then this is given as, what do you have here as your intercept? 1.4567. So you come here and write what? 1.4567. What is sign here? The sign here is what? Plus. What do you have here as the slope? 1.1964. The value you have here, or what you have here, is what? X, which is the independent variable. And we have been told that this independent variable is going to take a value of what? Of 10. So you are now going to say multiply by what? By 10. And whatever thing we evaluate from this becomes the test score of that student now when his reading or her reading hours is increased to what? To 10. or what we call the average performance of students when their reading hours what becomes what 10. It is better to answer it that way. The average performance of a student. That is getting some set of words the students now, and then asking them now to read now to increase their reading hours or what at 10. Then at the end now getting the average performance. That is what this thing means. The average performance of what of students when their reading hours is what is 10, not necessarily for a particular student. Now, when we now have now, it becomes what y estimate for what for 12 now is going to be 1.4567 plus 1.196 what for multiplied by what by 12. Whatever value you evaluate it here becomes is the average performance when the reading hours of the students are increased what to 12. So when it's increased to 14, we have what y estimate of what 14 is given as 1.4567 plus 1.1964 multiplied by what by 40. Whatever thing you evaluate it here becomes the answer. And without wasting much of your time for us now to be calculating and evaluating, we have computed and gotten these values now. So we are just going to call it up for you and then ask you to use your calculating device to cross-check whether what we have and what we are going to obtain are the same thing. Because the value which we have are given as the value which we have is given as the value is given as 13.4207. Here is 15.8135, and then here is 18.2064. That is the value that we have in those particular respective places. Sorry. Okay. So that is now how to get the values of what y when the values of the independent variable become 10, 12, and 14. Okay. So we now go over to the next question they ask us together. Next question they ask us is they said we should obtain the Pearson and the Spearman's correlation coefficients and explain your findings. Okay? That's what they ask us here. But before we go ahead now, we remind ourselves what we said about the correlation coefficients. When we talked about the regression, we said that in regression, one uses predicts the value of a variable using the value or values of other variables. And for you to make this prediction successfully, it has been established that there is a kind of relationship that exists between these independent variables and then the dependent variable y, or that exists between these variables. And for because we are discussing linear regression, we are saying that the nature of the relationship is going to be a linear relationship that is going to exist there. That's what we do in regression. But in correlation, we are trying to see determine the extent or the degree of this relationship that exists between these variables. And then two persons propounded a formula with which to obtain these values. The first person is what we call the Spearman. Yes, what we call the what? The Pearson. Yes, moment correlation coefficient. And the second person is the Spearman rank correlation coefficient. So we are going to mention give the formula for the first person, then use it to work, give the formula for the second person, and then use it to work. Thank you very much. So permit me to clean this place. Permit me to clean this place. And equally permit me to clean part of this data because the data is already in the table here. The formula that we gave for the correlation coefficients, the formula that we gave for the Spearman correlation coefficient is given like this. That R substitute what? X, Y. What we mean by R substitute X, Y here is because we are talking about simple linear regression where we have only two variables, one independent X the other dependent what y. We say that the formula is given as n summation of xy minus summation of x summation of y all over square root of what? N summation of x all squared minus summation of what? X all in bracket square. Open this bracket and close it. Open again. You have n summation of y squared minus summation of y. Open and what? Square it. Close the bracket this way. This is the formula that we say one can use to get the Pearson moment correlation coefficient. And of course, when we now come to this data, this thing becomes that what we have here becomes that this equals, here is my n and n is 7 here, so we have 7 multiplied by. Here is summation of xy, here is my xy, the sum is 161. I have what? 161. The sign here is what? Minus. Summation of x is what? 21, so I have what? 21 multiplied by. Summation of y is what? 42.5. So I have 42.5. Then all over. We have general square root of. Then here is my n, which still remains what? 7. But remember there is a bracket here. So you open the bracket. Here is what? 7 multiplied by. X squared is here. Here is my x squared. The sum of x squared is what? 91. So I have what? 91. The sign here is what? Minus. This is summation of x. Summation of x is 21. So I have what? 1. All raised to power what? 21. All raised to power what? 2. Close the bracket. Open again. What you have here is 7. You write what? 7 multiplied by. Here is y squared. We have not included y squared here. So you quickly come here and include what? Your y squared. Which means squaring all this value that is here. To square this, you have here to be what? 9. To square this, you have here to be 9. To square 5, you have here to be 25. To square 6, you have here to be 36. To square 7, you have here to be 49. To square 9, you have here to be what? 81. And then to square 9.5, you have, if you are squaring 9.5, you have 90.25. You have here to be 90.25. And when you sum all these values, what you are going to get is 299. Is 299.25. Is what you have. So what I have just done here is to include the variable y, be able to get e squares, because I have seen that I need to square it now for me to be able to evaluate this formula. And then this thing means summation of y squared. When I sum up my y squared, what I have is 299.25. So here becomes what? 299.25 minus. Here is summation of y alone, and summation of y is what? 42.5. So I have what? 42.5. But because it is squared, I will say raised to power what? 2. I will now close the brackets. This is what I have. So whatever thing you evaluate this thing becomes what we call the correlation coefficient for the Pearson moment correlation coefficient. Then the second formula is what we call the Spearman rank correlation coefficient. The Spearman rank correlation coefficient. Spearman rank correlation coefficient gave a formula like this, and I quickly give to you. It gave a formula like this, that its own formula is what? R is given as 1 minus 6 summation of di all squared all over what? N into n raised to power 2 minus 1. This is the Spearman's rank correlation coefficient, where this d square is the rank difference between the rank of x and the rank of what? Y. So for us to be able to evaluate this, what we are going to do quickly first of all is to come and rank x and rank what? Y in ascending orders of their values. And how do we rank observation? We rank observation starting from the rank of what? 1. The least observation in that variable takes 1. The second to the least takes what? 2, down to the last observation. That is how to rank. So if I want to rank x, I will come here quickly, and then I will now include another value. The value I'm going to include here becomes what we call R of x. What I mean by R of x is what? Rank of what? Of x. Then I'll come here. What is the least observation in this x? The least observation is what? Is 0. So that least observation, which is 0, takes the rank of what? 1. So here becomes what? 1. The next observation is what? 1, which means take the rank of what? 2. This one takes the rank of what? 3. This takes the rank of what? 4. Take the rank of what? 5. Take the rank of what? 6. And take the rank of what? 7. That is just what I have done. The least observation takes the least rank, and the highest observation takes the highest rank. So I will now come for what? For y. I want to rank the y. If you come here, you find out that I have the least observation to be 3, but 3 occurred what? 2 times. So I'm going to rank this 3 and rank this 3 as if to say it's the next higher observation. Then use the average of the 2 ranks now to be able now to assign to them. The first ranking of these 3 could have been what? 1. What I could have ranked this next observation could have been what? Could have been what? 2. But because these 3 and 3 are the same thing, I'm going to say rank of this plus rank of this thing divided by 2. So 1 plus 2 is what? Is 3. 3 divided by 2 is 1.5. So I'm going to rank this in 1.5 and rank this in 1.5. So when I have what? R of y, then I'll come here. I will have this thing like this. I have this thing like this. So here is going to be what? 1.5. Here is what? 1.5. I have ranked 1 and 2 already. The next least observation here is what? Is 5. So I'm going to rank that 5 what to be 3 because I've already used 1 and 2 ranks. So here becomes what? 3. Here becomes, next one is what? 4. Next one is what? 5. Next one is what? 6. And next one is what? 7. When I talked about what this D, I said that D is the rank difference. Rank difference means rank of X minus rank of what? Y. Before you now square it. So you are going to have a column that is talking about rank of X minus rank of what? Y. Then before you now say all square, that is what we call the D. So when you come here, you find out that here is what? 1 minus 1.5, which will now give you what? Minus 0.5. And minus 0.5 raised to power 2 will give you 0.25, positive number. So you have what is called 0.25. When you come here now, you equally find out that here is what? 2 minus 1.5. And that will give you what? 0.5. And 0.5 squared will equally give you what? 0.25. Then you come here. Here is 3 minus 3. Here is 0. 4 minus 4, 0. 5 minus 4, 0. Here minus 0. Here is what? 0. So what I did here was, if I get the rank difference by saying rank of X minus rank of Y, I will square whatever the result. That is what we are calling D. So when I said 1 minus 1.5, I had minus 0.5. When I squared minus 0.5, I had 0.25. Equally, when I came here, I had what? 2. 2 minus 1.5 gave me what? 0.5. When I squared 0.5, it gave me what? 0.25. When I came here, 3 minus 3 is 0. 0 squared is what? 0. 4 minus 4, 0. 0 squared is 0. So everything here becomes what? 0. Okay? So what I have now here becomes, I will now include this line like this. This sum here means I should sum the values I got for taking the difference between the ranks and squaring it. So I am going to sum everything here. And summing everything here will simply give me 0.5. Because the only thing I have here is 0.25 plus 0.25, which will give me 0.5. Then I'll quickly come here to calculate this. Then I have that R is equals now 1 because 1 is here minus. Here is my 6 times. The whole of this quantity here has become 0.5. So 0.15 all over. The value of my n is what? 7. So I have 7 into. Here is my n raised to power 2. So 7 raised to power 2 is here. Here 7 raised to power 2 minus 1. You close what's the bracket. Whatever thing you evaluate, this thing becomes what the answer. And without wasting much of your time, we have evaluated this and reported the answer. And evaluated this and reported the answer. And of course, it is going to be rational, not even rational. It is expected that the value of this and the value of this are going to be close, if not the same, because both of them are measuring the strength of the relationship existing between X and what? Y. The only difference is that while this one is using the 2 observations now, this one is using the ranks of the 2 observations. Okay? So what I'm now going to do, I will now going to call up now the answers here. So the answer for this particular one is given as, the answer for this one, which we have calculated for you, is given as 0.9861, and then the answer of this one is given as 0.991111. If you watch, you find out that the answers are very, very close. Very, very what? Close. In fact, when you keep these answers now in the two decimal places now, the answers automatically become the same thing. Because here, 1 comes here to be 9. You have 9. Here is what? 9. So the values are the same thing. So when questions begin to come up like, which correlation coefficient uses the two observations? Tell them it is the Spearman's, it is the what? The Pearson moment correlation coefficient. The Pearson moment correlation coefficient. It uses the true observations. Which of the correlation coefficient uses the rank of the correlation coefficient? The Spearman correlation coefficient, which is ordinarily called the Spearman ranks correlation coefficient. But when they want to ask you that question, they might not include the rank because they know you'll be able to understand what they mean. So when they ask which of the correlation coefficient uses the rank of the observations, it is the Spearman correlation coefficient. Which one uses the true observation? It is the Pearson moment correlation coefficient. So this is how now to obtain the correlation coefficient. So if you watch this value now and watch this value, you find out that there is a very strong relationship that exists between the reading hours and then the test scores. In fact, the relationship is very, very high. Okay? The relationship is very, very what? High. Oftentimes, they normally give what they call a scale. I don't know how true that scale is, but when they want to talk about this one is a strong correlation coefficient, this one is a weak correlation coefficient, and the rest of them. At times, they give us something like this. Let me just show you. They give us something like this. Let me clean this place. At times, they give us something like this. At times they say something like this, they give us something like this. Okay? Give us something like this, give us something like this. Here is my -1, here is my +1. At the center here is 0.5. So here is I have here and I have here. Okay? So they will now begin to talk about the values that lies from 0.5 down to what? To positive what? 1. And then perhaps the value that lies between 0.5 down to this -1. You understand? So when they give this thing now, they might equally come here and give something like maybe, let me say, here is maybe -0.25, and then here might be something like 0.75. Yes, 0.75, that kind of a thing. What we're just trying to establish here, but then I think let us not, because why we even need to skip it, that it has not been proven that when it lies between this to this is a strong positive relationship, and when it lies between this to this is a strong negative relationship, and the rest of them. So we might not even use this thing to make that statement we want to make. So forgive me about that. Let me clean it. Okay, so now these are the values of the correlation coefficient. So we quickly move over to the next question. That next question says, and I read, that next question says, I read, obtain the coefficient of determination. Obtain the coefficient of determination. Do you remember that in our last class we talked about the coefficient of determination when we say that it is the measure of how well our model predicts the dependent variable using the values of the independent variable? Or you can equally say that it is the measure of the variations that is explained by our model expressed in percentage. Or it is the measure of the variations that can be explained, the measure of variations in our dependent variable that can be explained by our independent variable. All this explanation I gave is about coefficient of determination. So when they begin to ask you questions, or maybe you are seeing a questions where they are saying, what is used as the measure of the variations in dependent variable that are explained by our model or by our independent variable. We are talking about the coefficient of determination. The coefficient of what? Determination. So I am quickly going to the board, write the formula for the coefficient of determination, then solve with you, and then make some explanations. So permit me to clean here. Okay? Permit me to clean here. Coefficient of determination. Okay? So our coefficient of determination I gave the coefficient of, let us write it with capital R raised to power 2, talking about coefficient of determination. So this is given as what? Beta estimate all raised to power 2, open a bracket, n summation of x all squared minus summation of what? X all raised to power 2, close the bracket, all over. Here is my what? N summation of y all raised to power 2 minus summation of what? Y all raised to power what? 2. This is the formula for getting your coefficient of determination. And of course, this thing becomes, we calculated this our beta estimate before and got 1.1964. So, and it is squared here, so you are going to say all raised to power 2, you open a bracket. N here is 7 times. Summation of x squared, look at your x squared. The summation of x squared is 91, so here is 91 minus. Summation of x is what? 21. So you have here now to be what? 21. All raised to power what? 2. You close the bracket. Then you have all over. Here is my 7 times. Summation of y squared is what? 299.25. So I have 299.25 minus. Summation of y is 42.5. So you have what? 42.5 all raised to power what? 2. Whatever thing you evaluate in this thing will be able to give you what is called coefficient of determination. And without wasting much of your time, we are going to call the true answer which we calculated and put it here for you now to be able to evaluate this and see whether what you are going to have is the same with what they have here. So the true answer from what we calculated is coefficient of determination is given as, the true answer is 0.9724. That is the true answer which we have there. But then there is a claim or a statement that is made, which of course we mentioned in our previous class. They say that in a simple linear regression, the coefficient of determination is the same as the square of the correlation coefficient. That's the statement they made. That in a simple linear regression, simple because only two variables are involved, the dependent variable and the independent variable. And then linear because the relationship between these two variables now are represented with a linear model and not like a curve. They told us that the value of the coefficient of determination is the same as squaring the correlation coefficient. And do remember that we have calculated the correlation coefficient before. And we heard that the correlation coefficient before is that our R of xy is given as the value of our correlation coefficient, which we got earlier, is that we had it now to be 0.9861. That was the value of the correlation coefficient. And of course, when we tested this thing now to actually know whether that statement is right or wrong, we told ourselves that the correlation coefficient, the coefficient of determination, R squared now, will now become what? R of xy all squared, which becomes what? 0.9861 all raised to the power what? 2. Shockingly, we had the answer to be 0.9724. Which means that indeed, when the correlation coefficient is squared, as long as that correlation coefficient is coming from a simple linear regression, the answer is going to be the same thing as the coefficient of determination. We solved these things that day. We mentioned that in that day, and that is what we have proven here. Do remember equally that we told us that there is another way of calculating the coefficient of determination when you are given what is called the sum of the squared regression and then what we call the total sum of a square. Last, in our previous class, we said that we have what we call our TSS equals RSS what R plus SS what E. What we mean by TSS is total sum of square regression. So you can even include R here or just total sum of squared. This is what we call sum of the squared regression. This is what we call sum of the squared error. We told ourselves that we can calculate the value of the coefficient of determination by saying that our coefficient of determination R squared is given as 1 minus. We have what we call our S what E all over what S what T. Why? Let us confirm whether this formula we wrote here is correct. Let me come here and clean these values. Of course, these are coefficient of determination. This is what the answer, coefficient of determination. We tried squaring the value of the correlation coefficient to know whether we can get this. We squared, we equally got that. We just want to give another formula for coefficient of determination in case, instead of giving you real data here, they tell you that some of the square regression is this and some of this is this. How do you go about that? So we clean here. What I wanted to prove, which is simple, is that we said that the coefficient of determination, which is R what squared, is given as the ratio of the sum of the squared regression all over the total sum of square. The ratio of the sum of square regression, which is S what R, all over the total sum of the square. That is the formula. But we know that from this formula here, but we now say but TSS is given as SS what R plus SS what E. This is given here. Okay? So making this SSR to be subject, we have that the TSS minus SS what E is given as what? SS what R. So I can easily come back here, wherever place I see SSR, I'll put it there, so that my R what squared now becomes, here is my SSR. It has become TSS minus SSE. So I have what? TSS minus what? SS what E all over. What I have is what? TSS. This becomes TSS all over TSS. The sign here is what? Minus. SS what? E all over what? TSS. This will cancel this to be 1, cancel this to be 1. 1 divided by 1 is 1 minus SS what E all over TSS, which is exactly what we gave here. So we are saying if they expect us to get the quotient of determination without giving us the observations now, for us now to calculate using that computational formula, but they have gone ahead to tell us that the sum of the square regression is this, and then the total sum of square is that. We should obtain the quotient of determination. We quickly apply this formula. Just tell yourself sum of the square error divided by sum of the square what total. Subtract it from what? 1. Whatever value you get becomes what is called coefficient of determination. Thank you very much. So we quickly run to the next question which they ask us. Let us run to the next question. The next question they ask us here is that they said you should obtain the residuals. Obtain the residuals when y equals 7 and then y equals what? 5. We should obtain the residual. Let me clean this board. Let me clean this board. Clean this board. They say we should obtain the residual when y equals what? 5 and when y equals what? 7. Of course, the residual is the difference between the values of the dependent variable from the predicted value of that dependent variable with your regression line. Residual. That is difference from the true value of the dependent variable and the predicted value. That's what we call residual. So they ask us to find the residual at y equals what 5 and y equals what 7. That's what they want us to do. Of course, another name of residual is error. So if they don't call this thing residual, they can call it what error. So we say obtain the error at the errors at the residual at y equals 5 and y equals what 7. So what you are going to do first of all is to predict the value of that y at y equals what 5 and y equals what 7. Know the value of their predicted values now before we begin to talk about what their true values. Let us return here and check. Where is y equals 5 here? Y is 5 here. So that place where y equals 5, x equals what? 2. So I will now come here and say y equals 5 at x equals what? 2. That's what here. When y is what? 5, x is equals what? 2. And remember that we got a model. The model we got was that y estimate is given as 1.4. Let me call it up correctly. What we had was a 1.4. The value we had was 1.4567 plus 1.1964x. That was the value that we had here. That was the value we had here. Okay. So what we are going to do is very simple. So we are trying to predict the value of what? Y when y is equals to what 5. And that at least when x is equals to what 2. So we now say here that my y estimate here is now given as here is 1.4567 plus here is 1.1964. The value of this x has become 2. I will say multiply by what? By 2. So whatever value I get here becomes the value of y when x equals what 2. So I will now come and say y equals what 7 here at x equals, when y is 7, what is the value of x? 4 is the value of x. When x equals what? 4. So I will now come here and say therefore my y cap is given as 1.4567 plus 1.1964 multiplied by this x has become 4 multiplied by what? 4. So you evaluate out this, you evaluate out this. Let us quickly write the value which we think we have down, and then know the value which we have. Then what the value we got here was when we predicted it here for this equals what, we had that this value is 3.8495, and we had this one to be that this is 6.2423. That was the value we had. The value of y when x is 2 is this, and the value of y when x is what 4 is this. However, we know very much well that the real data is saying that when x is 2, that y should be 5. But what we are getting here that when x is 2, our predicted value is what? 3. So what we are now going to do now to get the residual is that the residual for here now, my residual now here, my residual, or what we call the error term, let me represent it with what? Error. Okay? And let me put it now, the error term I'm going to have when y is what? 5. When y is 5. Y is 5 is given as, here is what? Y minus what? Y cap. The question is, what is my y? My y here is what? 5. This is equals to 5. What is my predicted value when y is 5, which is at that point in place where x is 2? It is 3.8 something. I have 3.8495. So this minus this will be able to give you the residual at this y equals what? 5. So at my error 10 now, when y is equals to 7, is now going to be, I'll come here. I say, of course, what is my value of y here? It is what? 7. So I will now write what? 7 minus. What is my predicted value at that point in time when y is 7, which corresponds to when x is equals to 4. It is 6.2 something. So I have 6.124 towards 3. Whatever value you get here now is what we call the residual. So the residual is different from the true values of what a dependent variable from their predicted what values at that particular point. That is what we call the residual. Okay. There are so many things that you ought to know about the regression which we looked at here. Okay. So when we calculated the coefficient of determination, we had a high value of the coefficient of determination. We equally had a high value of what of correlation coefficients, telling us that there is a strong relationship between the reading hours of students and then their test scores. Okay, so but we remember that we say that the coefficient of determination is always often expressed in the percentages. So that time we had 0.9 thereabout. If it's multiplied by 100, we are going to have something about almost close to 99%. And someone begin to say that 99% or whatever value now is variations in the response variable can be determined or explained with our model. So thank you very much for your audience in the class. We still look forward of going to call up other questions from a regression and solve them together with you. But a situation whereby you found the little things challenging in this work we did, please, I plead with you to visit our first class that is tagged on YouTube as a class on regression and correlation 1. This one might be tagged as problem solving on the regression and correlation 1. Thank you very much. Wait till we meet in our next class.